Hi folks, this is lesson 2 on properties of derivatives. Now I want to take a look at an example here. So let's say we consider the derivative of the function 2x. Okay, now you can definitely put this into the limit definition to determine the derivative, but we'll do this intuitively here since this is just the line 2x, okay, meaning that the rate of change is constant. So since the slope is equal to 2, meaning the rate of change at all points on this line is a constant of 2. So we know that the derivative of 2x should just be equal to 2. Okay. Now, remember what we're trying to do here is we're trying to find a way to determine derivatives by breaking them up into simpler derivatives. So when I look at this derivative of 2x, I can see it in two ways. You have shown, at least in the last video, you should have shown afterwards that the derivative of the function x is just equal to 1. Of course, intuitively, we can also see that this is going to be the case because this is just a line of constant rate of change 1. Okay, and I notice here that the derivative of 2x is just twice that amount. Okay, so it looks like the derivative of 2x is equal to 2 times the derivative of x. Okay, so this implies, or we can conjecture, that this might lead to a bigger property. Can we say in general that the derivative of a constant times a function is equal to just that constant times the derivative of the function? Okay, so this example here seems to indicate that this might be possible. Now this is a real help because then if we know what the derivative of x cubed is, we'll also know the derivative of 3x cubed, 4x cubed, 10x cubed, negative 7x cubed. Okay, once we find the derivative of, say, 4 to the x, then 2 times 4 to the x should also be easy to find. So the idea here is that if you're just multiplying a function by a constant, is that the same as just multiplying that constant to the derivative of the function. So this is one of the things that we're going to be proving in this video. Now if I take a look at the derivative at 2 to the x in another way, I also notice that the derivative of 2 to the x, okay, is equal to the derivative of x plus the derivative of x. Now you might say, well, this is essentially saying the same thing, and yes it is, but it's looking at it from another perspective. Can I say that the derivative of the sum of two functions, okay, is that going to be equal to the individual derivatives? Okay, well, that would be very useful because when we start combining functions through addition, for example, you think of polynomials as really just a combination of simpler functions. So when we have 3x cubed plus 2x squared minus x, can we just find the derivatives of those simpler individual terms in the polynomial instead of, again, taking a whole polynomial and putting it into our limit definition? So these are the two properties that we're going to hope to prove here. Okay, so let's start with the first one. Okay, so here let's try to find the derivative of a constant times a function, and let's see if we can prove that it's equal to the constant times the derivative of the given function there. Okay, so since we want to actually do a proof, we're going to have to use a limit definition. So we know that this is going to be the limit of, as h approaches 0, of this function here evaluated at x plus h. So c is just a number, so it's not affected by the input. So this is c times f at x plus h. And then from there we have to subtract the function at x. So c of f at x all over h. Okay, so take a look at what kind of algebra we can do, and we see that these two terms both have a common factor of c. So I'm going to factor out the c, and I'm left with here f at x plus h minus f at x all over h. Okay, But remember, this is a limit here, and I want you to go back to your limit properties and see that one of our limit properties was that the limit as x approaches a of a constant times a function is just equal to the constant times the limit of the function itself. Now, why does this apply here? Because remember that the limit of this expression is itself a function, because x is varying. In fact, it's just the derivative function. Okay? So, by the limit properties, I can just remove this constant outside the limit. And this expression here is just the derivative function of f. That's how it's defined. So we can say that this is equal to, and by the way, we should specify here by limit properties. Okay. Okay, so this is just equal to c times the derivative of the function f at x. Okay, which is exactly what we wanted to prove. Okay. One little thing we need to specify here, because we need to see if there's any conditions on this here. And in order to use this limit property, the condition is that the limit has to exist. Okay, so this limit here has to exist in order to use our limit properties. Okay, but this limit existing means the derivative of f has to exist. Okay, so this only works if f prime at x exists. Okay, if that limit exists. Okay, so this is good news, because now we're sort of on our way of proving that we can take a more complex function and start reducing it to simpler forms. So if you have a function that's multiplied by a constant, you can now just remove the constant and find the derivative of the simpler function. So for example, we had found in the last example, we found that the derivative of x squared plus x was equal to 2x plus 1. Okay? This was where we first had this idea that perhaps the derivative of a sum is equal to the sum of the individual derivatives. But now, let's say I want to find, okay, so let's call this an example here. Let's say I'm looking for the derivative of 3x squared plus 3x. Well, that's just equal to the derivative of 3 times x squared plus x. I don't have to go through the whole rigmarole of putting this function into the limit definition, because I've already determined, and that should just be an x there, I've already determined the derivative of this function here. So by the constant rule, okay, that we've found above, I can rewrite this as 3 times the derivative of x squared plus x, and I've already determined this derivative. So I don't have to repeat that whole process. Okay, so this is an example of the usefulness of this constant multiple rule. Okay, we've already done the work to find the derivative of the simpler function. We can now use that to find the derivative of this slightly more complex function. Okay, so it would be great if we can take this further and show that we can just break up x squared plus x into its simpler terms. Okay, in other words, show that the derivative of a sum of two functions is just the sum of the individual derivatives. So let's see if we can actually prove that. Okay. So our goal here is to determine the derivative of the sum of two functions. Okay, so again, we have to put this into our limit definition. Okay. So as h approaches 0, so we look at this as one function. So again, think about what you did with combinations of functions and advanced functions. This is now some new function. So first I have to evaluate this function at x plus h. So that'll be the first thing I do, and I know that I just do that by evaluating the individual functions at x plus h. So f at x plus h plus g at x plus h. Okay, and then I subtract the functions evaluated at x, so minus f at x plus g at x. all over h. Okay? So here now we have to sort of think about how we're going to deal with this here. Remember, our goal is I'd like to show that this derivative is equal to the derivative of f plus the derivative of g. Okay, so my goal here, and we'll see this come up on other occasions, is I want to try to rewrite this expression by trying to join together everything that has to do with f and everything that has to do with g. And I want to separate those out, because remember, our goal is to eventually write these as two different derivatives, one of f and one of g. Okay, and this one here is pretty straightforward. So I'm going to take everything to do with f in one bracket. So here I have f at x plus h, and then from that other bracket I'm going to have minus f at x. Okay, and then in the other bracket I'm going to have g at x plus h, so here plus, so g at x plus h. Okay, and then here I've got minus g at x all over h. So now I can go further. I can just split this up into two fractions. Okay, so here limit as h approaches 0 of f at x plus h minus f at x all over h. Okay, plus g at x plus h minus g at x all over h. Okay, so now I've written this as the limit of this expression here, which hopefully you recognize is the expression that's in the derivative of f, plus this expression here, which is part of the derivative of g. But this is the limit of the sum of two functions. So again, by our limit properties, we can write this as the limit of each, the sum of the individual limits here. But again, the limit properties tell us that we can only do this if the individual limits themselves exist. Okay? So when we give this property, we're going to have to assume that these two limits exist. Now, for this limit and that limit to exist, essentially means that f has to have a derivative and g has to have a derivative. Okay? So this only works if the limits exist. Okay, sorry about that. That is, if the derivatives exist. Okay, so if they do, so we'll have to assume this when we're writing out our note. We can write that this is equal to the limit as h approaches 0 of f at x plus h minus f at x all over h, plus the limit as h approaches 0 of g at x plus h minus g at x all over h. And this first expression here just represents the derivative of f with respect to x, and this second limit here represents the derivative of g with respect to x. Okay, so here, we'll use the same notation when we write out our note, but essentially this tells us that the derivative of the sum of a function is equal to the sum of the derivatives. Okay, so slowly we're getting to the point where we can definitely find the derivative of any polynomial function. Because what is a polynomial function made up of? Well, it's just some exponent of x times a coefficient plus or minus other terms. That we still are going to want to try to determine is there a nice way of determining a formula for any power of x? In particular, any positive integer power of x. Okay? So far we've done x squared, we've done x cubed. Okay, but you can see that x to the fourth, x to the fifth is just going to get more and more complicated. So one of our big goals that we're going to do next class is to see if we can figure out a way to determine more easily, in other words, without having to use limit definition, the derivative of x to the n. Okay, and if we can, then we'll be set. We'll be able to determine the derivative of any polynomial function. Okay, so what you should be doing as an exercise here is you should be proving that the derivative of the difference of two functions is equal to the difference of the individual derivatives. Okay, since addition and subtraction are so closely related, it shouldn't be surprising that if this works for addition, it should also work for subtraction. Okay, so you should try to go through this proof, preferably without looking at the one we just did, but if you need to take a look, no problem. And anytime you're giving a proof, you also restrictions. Okay, what conditions do you need to have in order for that proof to work? Okay, so there'll be one last part to this lesson, but try to get this done first.